Okay, welcome back to Statics 1. In the last lecture we talked about the concept of a free body diagram where you essentially take the member and describe all of the forces acting on it, and presuming that it's in equilibrium, we can write the equations describing equilibrium and solve for the support reactions. And we haven't actually walked through that entire process. So I want to present one example, and this is actually an example from the textbook that we're going to be looking at. I have the textbook in front of me, and let's go ahead and get started. And this is a good way to show you like how I handle notation, how we do the write the equations and that kind of thing. So the problem is a very simple one in which we have a beam, of course. Well, not of course. But we have a beam, and the beam length is 7 meters across, and it's actually, I'm going to draw here, there is a loading over here, and this is 100 newtons. 100 newtons. And this is a distance of 2 meters. And then we have over here another odd force coming in at a 45-degree angle at the top of the girder. Right here. I'll put it right here like this. And this is at a 45-degree angle relative to the horizontal. That is 600 newtons. And the dimensions, let me finish this up. This is 2 meters. In other words, from the left edge to this point here is 2 meters. And then this distance in the middle is 3 meters. Okay, and the supports are a rocker at one end. So we have at this end a rocker at one end, and at the other end we have a hinge. And you remember the difference between a hinge and a rocker is that the rocker allows for horizontal movement. The hinge does not allow for horizontal movement. So that's why this one's going to have 2 support reactions, and at this end we'll only have 1 support reaction. It'll be an entirely identical problem, at least analytically, if we put a roller down at this end. Although a rocker and a roller obviously are physically different components. Let's see if we got everything. I do, and we're going to assign letters to each one of these points. And I'll follow the notation in the book. Oh, and there's one more thing that you should know, which is that the beam depth is actually 0.4 meters. And so the half depth, which will be important, is 0.2 meters. So 0.2 meters from the top of the girder to the midpoint. So we'll call this point A. And the other one down at the other end is B. And this point here we're going to call D. And I don't know why they didn't have a C. I'm just following the notation in the book. We could, of course, call this C if we wish to. And I'll add it there just so we know. So A and B at either end, C at that point, and D at that point. All right, so let's draw our free body diagram. In this case, the free body diagram is pretty much the same. This is a rocker. And this on this end, and I should probably draw it like more fixed. So this is really fixed. This is a hinge. So the rocker is going to have only a vertical component. And the notation that I would typically encourage you to use would be if you have a designation A, we're going to call that force A sub y. So this is a force A sub y, and the magnitude is, well, it's a force vector with a magnitude A sub y. And I typically will draw these in the positive direction, even if you know, for example, that or if you have an intuition that the direction of the force, and you can draw it in that direction. But what I would encourage you to do is draw these so you have positive y values and positive x values. So let me show you that one. This one is kind of obvious, and in fact, we would expect the support reaction to be up because the forces are all down. But on this end, I'm going to put our force. One force we're going to have is in the horizontal direction. Remember I said the hinge is preventing the movement of this beam. So we have this force. We're going to call this Bx. And in this case, if you look at it, we have a force in this direction. So most likely what we're going to do is when we calculate this, we're going to end up with a Bx value negative magnitude, which means that as we drew it was incorrect, and in fact it's actually pointed the other way. But we see what I've done. I've drawn it basically in the positive x direction. That's my suggestion to you. And then I'm going to draw a B sub y here. And again, so that's my vertical support reaction at that end. And then we have to finish out our, in other words, the free body diagram is not just the support reaction, but you have to have the imposed loads. So we'll have this 100 newtons here. And over here we can break this into its x component and y component. And I encourage you to do that because it'll make it easier when we calculate the sum of the moments. So at this point here, which we call C, we're going to have a force acting in the x direction, and you can see it's going to be, the x component will be 600 newtons times cos 45, because it's the the force that's adjacent to the 45 degree angle. So this will be 600 newtons times cos 45. That's the x component. And then the y component, and because we've drawn this, in this case, you see that I'm not necessarily drawing it in the positive or negative, in the positive x direction or positive y direction. I'm following the convention from the problem itself. So we know in this case, we're going to have a vertical force. If this one's 600 newtons cos 45, the horizontal, then the vertical will be 600 newtons times sine 45. And it turns out, of course, well, you may not know this, sine 45 and cos 45 are the same value. So in fact, the x and y components of this will be the same. Now your free body diagram should also show the dimensions. So we'll just copy those from above. So we have 2 meters from A to C, and then we're going to have 3 meters from C to this point, which we call D, and 2 meters from here to here. And don't forget, of course, that we do have a vertical dimension here, and this is 0.2 meters. Okay, so that's the problem. So here's the original diagram showing the beam and its supports, and then this will be the free body diagram. Okay, so now we can actually solve this. And what I'm going to do is, we're going to take this and we're going to write our equilibrium equation. So you probably remember that from 2 lectures ago. I'm going to write that over here, and I'm going to say that the sum of the forces in the x direction equals 0. Now let's write all the forces in the x direction and try not to forget any of them. So we're going to end up with this one, 600 newtons times cos 45. So we don't, 600 newtons times cos 45 degrees. That's our first x component. The other x component we have is bx. So this is going to be plus bx. So 600 newtons times cos 45 plus bx equals 0, you can see right away, hey, we can solve for bx right away. So this is essentially enables us to do part of our solution immediately. So it's always good to focus on, as you're writing these things, to think about it. And in fact, if you think about it, 600 newtons, this is going to be a positive value. We're going to have bx is going to be a negative value. So in fact, what we find is that the direction that we drew it, in other words, in the positive x direction, is in fact incorrect. And the correct support reaction is a force acting towards the left. All right, so now we're going to do this in the y direction. And here we have a few more forces. So we have f of y equals 0. Or excuse me, the sum of f of y equals 0. So we're going to add up, we have this one, 600 newtons times sine 45, acting downward in the negative direction. All right, where else do we have? We have our 100 newtons acting downward in the y direction. And we have two support reactions, AY and BY, and they're drawn in the positive direction. So I'm going to add them on the next line, plus AY plus BY. And actually, if you look at this, you realize you have an equation, you have two unknowns, so we can't actually solve for this yet. We have to add one more equation, and that equation is going to be the sum of the moments. And we can actually pick the point where we evaluate this. And what I typically will do is I'll pick a point where we have the most unknowns. So for example, and I'll explain in a minute why I do that. So what I would look here you have bx, by are both unknown. If we evaluate the moment at this point, then when we write that equation, the sum of the moments, it will not include components with bx and by in it. So then we'll be able to solve. Everything else is known, all the dimensions, except ay. So then we'll be able to solve directly for ay. And then we'll substitute that into this equation, and we'll solve for by. So that's what I'm going to do. So I'm going to write here the moments. You see the sum of the moments about point B. So what are they? And we have 1, 2, 3, 4 forces that are going to be causing moments about point B. So we can do those. Let's make sure we don't forget any of them. And remember, when you're doing this, that you do them in the right direction. So clockwise rotation is negative, and a counterclockwise rotation is positive. So here we have, let's start here with AY. AY going vertical, and a moment arm in this case would be 2 plus 3 plus 2, 7 meters. And in this case, you can see that if we're rotating from here, rotating upward in this direction, that's essentially a clockwise rotation. So I'm going to put a negative value here. So it's going to be negative equals negative AY times 7 meters. Okay? So the next one, let's look at this one. 600 newtons, sine 45, and it's actually acting in a counterclockwise direction, right? If it's pointing downward, and we hold this point, we fix this point, that's going to cause a counterclockwise rotation, right? From 12 towards 9 rather, and then towards 6. So that's a counterclockwise, so it's a positive value. So I'll put here plus 600 newtons sine 45 times, I think I'm running out of room. Hold on, I have to see where my camera is. And times 5 meters. All right, so I'll put parentheses around these so we understand. And you can see the units are going to be Newton meters, right? For moments, that's exactly what we'd expect. The units of moments are going to be a length and then a force unit. And then, so the force have only units of newtons, which so entirely makes sense. So I'm happy with that. let's see what we have. So we have that term, 2 in there. So we did this one, we did this one. Let's do this one. So we have 100 newtons. And in this case, it's again, the rotation is going to be counterclockwise because we're pushing down on this moment arm. So it's 100 newtons times 2 meters. So it's going to be plus 100 newtons times 2 meters. And the last one that we have to look at, and this one some people frequently forget about, and sometimes you'll see the problem will say neglect the thickness of the beam, because this one does not have a very big moment arm, this horizontal component here. The moment arm is actually only the 0.2 meters. And the way to think about this is remembering that you have your line of action. Remember, whenever you're calculating moments, you take the line of action and you extend it, and then you figure out where that perpendicular distance is. So I'll extend my line of action. And so here's the moment arm here. Is this 0.2 meters. Because that's how you solve for that moment. So I'm going to write here, and is the direction positive or negative? So here's my moment arm. I'm going to fix this point, and we're pushing this way. So I'll do it with my arm. You're going to push this way, and you're causing a rotation in the clockwise direction, which would be negative. So we're going to put here minus 600 newtons times cos 45 times 0.2 meters. All right, so let's look at this, and I'm not actually going to do all the algebra. So we have 3 equations. The sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0. And the sum of moments, and we selected point B, remember. And you'll notice that we only have one unknown, which is great. So I'm not going to do the algebra, but we can see that we have one unknown, otherwise all these other values are known. So we could solve for AY here. It's just algebra, right? And we know from this one we only have one unknown. So we can solve for BX in this case. And then this one we have a linear equation with 2 unknowns, AY and BY. We know A sub Y from this equation. We can substitute that in here. So we know AY and we can solve for BY in this instance. So we had 3 equations, 3 unknowns, which you can, as long as they're linear, you can always solve for all the values. All right, so this is a really good example of typical type of problems with free body diagrams, where we have a rocker at one end. It could have been a roller as well. It would be essentially the same calculations. At the other end, we had a hinge. And we wrote the 3 equations. Sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, sum of the moments equals 0, and then we could solve for the 3 support reactions that came up in our free body diagram. You see 1 unknown, 2 unknowns, 3 unknowns. So that's the whole, this is a very good sort of typical problem. And if you have any questions on this, be sure to send me an email. Otherwise, I will see you in class.